If you've got a system of linear equations, like let's for example say x plus 2y is equal to 1 and 2x plus y is equal to 2, then you might solve this system of linear equations by, for example, subtracting a multiple of the first equation from the second equation to eliminate x, and then multiplying the resulting equation by a constant, so it said y equals something. So when you can do this, you can find all the values of x and y which satisfy the given system of equations. But we know how to represent our systems of linear equations in a matrix form, and what we're going to look at in this video is what manipulation to this matrix form corresponds to the kinds of things that we do to systems of linear equations when we want to solve them. So when we do manipulate a system of linear equations, we don't just change the left-hand side, you have to change both sides. So you have to do the same manipulation to both sides of the equation if it's going to be true. But the way in which we represented our linear systems was like this. We represented a linear system of linear equations as a matrix equation ax equals b. So we don't just want to manipulate a, we want to manipulate a and b together. So for this reason, we introduce a new matrix which combines a and b into one matrix, and it's called the augmented matrix of this matrix equation. What it is just a with b added as an extra column. So the way this is written, this augmented matrix is sometimes written like this, or sometimes like this without a bar. It really doesn't matter, it doesn't make any difference. So I will usually use the second term form. If you want to do something different, go right ahead. So let's take a simple example. So perhaps we have a system of linear equations that looks like this. 2x plus y is equal to 1. So in the matrix form of this equation, we would have a being equal to 1, 2, 2, 1, and we would have b being equal to 2, 1. So the augmented matrix for this system, which I'm going to write like this, would just be a with b added as an extra column like this. Okay, so really simple. That's how we define the augmented matrix for a matrix equation in the form ax equals b. Now, here are the three different kinds of manipulation which we often do to a system of linear equations when we're trying to solve them. We might add a multiple of one equation to another equation. We might multiply both sides of an equation by a constant. And we might want to change the order of our system of equations. So we might want to swap the order of two equations. The way which the resulting things that would happen to the augmented matrix of a system are called row operations. And so those row operations come in three types corresponding to the three different kinds of manipulation I've been talking about. So the first type of row operation that you can do to a matrix is you can add some multiple of one row to another row. So if you want to add lambda times row I to row j, then we have some notation for that row operation. We write it like this. So let's look at an example of doing that. I've written a matrix at the bottom here, and I'm going to do this first type of row operation to that matrix. So I'm going to do the row operation where I add 2 times row 2 to row 1. So row 1 goes to row 1 plus 2 times row 2. So the result of doing that, well, row 2 wouldn't change, and row 3 wouldn't change. And the one that would change is row 1 would change, and it now becomes row 1 plus 2 times row 2. So that's 1, 2, 0. Okay, so that's the first type of row operation. You add a multiple of row I to row j. So here we added 2 times row 2 to row 1. The next type is when we multiply a single row by a non-zero number. Now it's important that this number must be non-zero because the new equations won't have the same solutions if you multiply them by 0. You've just got rid of one of your equations if you multiplied it by 0. So in our row operations we only allow multiplying by a non-zero number. So let's look at what would happen if we did this in our example. So here this time we're going to multiply row 3 by 2. So the notation for that is row 3 goes to 2 times row 3, and the result in this case would be, well, row 1 wouldn't change and row 2 wouldn't change, but row 3 will become 2 times 0, 2 times 0, and 2 times 1, like this. Okay, Right, so our last type of row operation, then type 3, is the row operation where you swap two rows. So again, in our example here, let's say we're going to swap row 2 and row 3, and the notation for this is row 2 and then this two-headed arrow and then row 3, like this. So the result will be that row 1 didn't change, so row 1 stayed the same, but this time row 2 becomes row 3 and row 3 becomes row 2. Alright, those are the three different types of row operation which we can do to a matrix. And there is something interesting to notice about these row operations, and something very important, which is that the row operations are invertible. So if you give me any one of those three row operations, there's another row operation which takes you back to where you started. So for example, if we have the row operation which adds lambda times Ri to Rj, then we can get back to where we started by subtracting lambda times Ri from Rj. So let's look at an example again. If we take, yet again, starting off with our identity matrix, and if we do the row operation which adds, let's say row 1 goes to row 1 plus 2 times row 2, then we get, well, row 1 would change and we'd end up with 1, 2, 0, and then the other rows wouldn't change. And of course we can undo that just by subtracting 2 times row 2 from row 1. So the row operation which sends row 1 to row 1 minus 2 R2 would take us, if you think about it, back to where we started. Okay, so row operations of the first kind are invertible. For any such row operation, there is another row operation which gets you back to where you started. And of course, the other row operations are invertible as well. So if you multiply row I by the non-zero constant lambda, then you can get back to where you started by multiplying row I by 1 over lambda. So again, let's just have this example. So if we do 1, 0, 0, 0, 1, 0, 0, 0, 1, the 3 by 3 identity, and if we do row 1 goes to 2 times row 1, then the result would be that row 1 changes, but all the other rows stay the same. And if we want to undo that, if we want to get back to where we started, then of course we can do that by doing the row operation which multiplies row 1 by a half, by 1 over the thing we originally multiplied it by. When we multiply by a half, we of course get 1, 0, 0, and then nothing else changes. So you can see we genuinely are back where we started. And for the last type of row operation where you swap two rows, so for example you might swap row 1 and row 2, of course you can get back where you started by swapping row 1 and row 2 again. So this final type of row operation is self-inverse. It is its own inverse.